we selected two redundants. So one is VB, another one is VC. So therefore we have to use two compatibility equation to solve, to determine VB and VC. So compatibility equation, it may be a slope is equal to 0 or a deflection is equal to 0 generally. So in our case we selected VB and VC, both are forces. So forces means we have to select deflection is equal to 0. So some other case you may select moment also redundant. In at that case comparative equation will be, at that point rotation will be 0. Okay, so in this case we selected VB and VC as a redundant, so therefore deflection at VB and deflection at VC is equal to 0. These two are our compatibility equation. Now apply principle of least work, okay, or theorem of least work. What is theorem of least work? For every indeterminate structure which is loaded up to the limit of proportionality, the total strain energy is minimum. Okay, so this is our theorem. Okay, so from the theorem, dou u by dou v b equal to 0, that is first compatibility equation. Then dou u by dou vc is equal to 0, that is second one. So u means a strain energy. So since beam is a flexural member, so it is mainly subjected to the bending moment. So therefore strain energy stored in a beam is equal to m square dx divided by 2a, m square dx divided by 2ea. So now substitute strain energy in above equation. The final equation will be dou u by dou vb is equal to integration of mx dou mx divided by dou vb into dx divided by a equal to 0, first equation. Then dou u by dou vc is equal to integration of mx dou mx divided by dou vc into dx divided by ea equal to 0, second equation. Okay, so try to solve these two equations. With the help of these two equations we can determine VB and VC reactions. Okay, so first what to do? First we want to derive the expression of mx at each segment of the beam, each portion or segment of the beam. Then partial derivatives of mx with VB and VC also determine. Okay, so it can be represented in a table like this. Okay, so first one is segment, then origin, then limits, then mx, then dou mx by dou vb and dou mx by dou vc. Okay, so in this case, so first thing what should we do means, so first we have to determine the support reactions. Okay, support reaction in terms of both external load and redundant. So our case we selected VB and VC as a redundant, so therefore that beam is like become a cantilever beam. Okay, now I start writing the equation from the right side, so therefore there is no need of determining the reaction VA and MA. Otherwise you have to determine the support reaction in terms of both external load and redundant. Okay, so first consider segment DC. Okay, consider segment DC. So take section XX, x distance from point D. Okay, so segment is DC, our origin is D, then limit is C, D to C is 2 meter. Okay, 0 to 2. So what is the moment equation? So moment, we know the sign conventions of moment. Sagging moment will be positive, hogging moment will be negative. So this is our section. So like this, the sagging moment means this is positive. Sagging moment means thickness positive, hogging moment means negative. So our case, so at the for the segment DC, so moment will be, so right side of the section XX will be minus 20x. It is a hogging moment, so therefore minus 20x. Now differentiate this mx with the VB, partial differentiate mx with VB, which is equal to 0, then partial differentiate mx with respect to VC, again it is 0. Then consider segment CB. So origin I take an origin as d, origin d. So therefore our limit will be 2 to 6. So you may take origin as c also. So c means, so x will be this distance. So if you take c as origin means, so this distance will be x. Okay. So in this case limit will be 0 to 4. Okay. But I take an origin from d, so therefore x is measured from d to section xx. Okay. So therefore limit will be 2 to 6. Then bending moment equation will be 20 into x, that is hogging moment. Then Vc creates sagging moment, so therefore plus Vc into x minus 2. So again differentiate with respect to Vb. So mx, there is no Vb term in mx, so therefore dou mx by dou Vb is equal to 0. Then dou mx by dou Vc is equal to x minus 2. Then consider segment BA. Consider segment BA. So in this case also I take an origin as a d. So therefore limit will be, so 2 plus 4 6, 6 to 10. So limit will be 6 to 10. Then bending moment equation will be, so first, so 20 kN force, it creates hogging moment minus 20 into x. So minus 20 into x. Then Vc creates sagging moment, Vc into x minus 2. Vc into x minus 2. Then third force will be Vb. So Vb also creates sagging moment, Vb into x minus 6 plus Vb into x minus 6. Then finally 40 kN per meter UDL. So it creates hogging moment. So its value is 40 into x minus 6 into x minus 6 by 2. The final term is like this. Then differentiate, partially differentiate with respect to Vb means x minus 6. Partially differentiate with respect to Vc means x minus 2. Okay. Now substitute above expression in equation 1 and 2. So what is our equation 1? So equation 1 will be integration of mx dou mx divided by dou Vb into dx divided by a equal to 0. Okay. So dou u by dou Vb is equal to, so the beam has 3 segments. Okay, one is DC, then CB, then BA. So add these 2 segments and then finally is equal to 0. So dou u by dou Vb is equal to integration of DC mx dou mx divided by dou Vb into dx divided by EA plus integration CB mx dou mx by dou Vb into dx divided by EA plus integration BA mx dou mx divided by dou Vb into dx divided by 2a equal to 0. Okay, substitute all the terms. So in the DC portion, so mx moment at the section xx is equal to minus 20x, then dou mx divided by dou Vb is equal to 0. Then for CB portion, mx will be this one minus 20x plus Vc x minus 2. Then dou mx divided by dou Vb, which is equal to 0. So in the mx term there is no Vb, so therefore integration as a partial differentiation with respect to Vb is equal to 0. Then BA portion. So BA portion, so it has moment of inertia of 2 times. So DC and CB have a single time moment of inertia, but BA is 2 times, therefore denominator is 2EA. Then mx for this portion also, portion is equal to minus 20x plus Vc into x minus 2 plus Vb into x minus 6 minus 20 x minus 6 square. Okay, so into dou mx divided by dou Vb, which is equal to x minus 6. Finally this term is equal to 0. Okay, now expand this equation. Okay, so in the first term in the DC portion, so different partial differentiation of AB is equal to 0, though mx divided by though AB is equal to 0. So therefore this is cancelled. Then second term also 0, this is cancelled. So finally 1 by 2a integration limit 6 to 10, that equation remains. Okay, now expand it, then finally integrate it. It gives an equation in terms of VB plus VC, some coefficient times VB plus some coefficient times VC is equal to some constant. Okay, so this is taken as equation 3. Okay, you may solve this equation with the help of calculator also, you may try. Okay, so or manually expand it, then integrate it. Okay, this is equation 3. Then substitute in equation 2. From the equation 2, we know that dou u by dou vc is equal to integration of mx dou mx divided by dou vc into dx divided by ea equal to 0. So this is general equation. So the beam, it is a 2-span continuous beam, it has 3 segments, so therefore integration of dc portion plus bc, then ba equal to 0. Then again substitute all the terms. Okay, so in the dc portion mx will be minus 20x dou mx divided by dou vc is equal to 0. Then bc portion, so limit 2 to 6, mx minus 20x plus vc x minus 2, then dou mx divided by dou vc is equal to x minus 2. Then ba portion, limit 6 to 10, moment mx is equal to minus 20x plus vc x minus 2 plus vb x minus 6 minus 20 x minus 6 square. Okay, into dou mx divided by dou vc is equal to x minus 2. Then moment of inertia of this portion is 2i, so therefore denominator will be 2ea. So finally this term is equal to 0. Then finally you may integrate it. Okay, expand the terms and integrate it. The final equation will be 26.67 VB plus 96 VC is equal to 4213.33. This is equation 4. Okay, now solve equation 3 and 4 by calculator. Okay, manually. Okay, so we get VB is equal to 50 kilonewton, VC is equal to 30 kilonewton. So for solving these two equations we may use matrix approach also. Okay, so this equation 3 and 4 constitutes a linear simultaneous equation. It may be represented in a matrix form. Okay, so that is 10 matrix A x is equal to B, like this form. So x is equal to A inverse B. Okay, so from that finally VB and VC is equal to 50 and 30 respectively. Okay, and up to this we determine the redundant reactions. Okay, so our aim is to draw the shear force and bending moment diagram. Okay, so for this, so first we have to determine all the support reactions. Okay, so we determine 2 support reactions in the previously. So another 2 support reaction is determined with the help of equilibrium equation. So now draw the diagram. Okay, so apply equilibrium equation. So in this case it is a coplanar parallel system of force. So there are 2 equilibrium equations, summation of V equals 0, then summation of MA equal to 0. So first apply summation of V equals 0 means, so what are the vertical forces are available? So VA is in a positive direction, positive upward direction, upward direction taken as positive. Then VB, BC also positive direction, upward direction. So VA plus 50 plus 30. Then downward forces means, so one is the UDL. So UDL is 40 kN per meter. That length is 4 meter. So 40 into 4 is the total load acting in the downward direction. Then so another one point load is 20 kN. It is in downward direction. Therefore minus 20 equal to 0. Finally VA is equal to 100 kN. Then apply second equilibrium equation. Summation of moment about point A is equal to 0. Okay. So we consider the moment. Okay. At point A is anti-clockwise direction, so therefore minus MA. Then UDL. So UDL it's create clockwise moment about point A. So therefore plus 40 into 4 square by 2. Then VB reaction creates anti-clockwise moment. So therefore minus 50 into 4. Then VC also anti-clockwise moment minus 30 into 8. Then 20 kilonewton force it creates clockwise moment. So plus 20 into 10 equal to 0. Finally M is equal to 80 kilonewton. So it's in positive value means our assumed direction is correct. Okay. So therefore the support reaction will be hogging moment. Okay. So before we are going to draw a shear force and bending moment diagram. First draw the free body diagram. It may or may not be necessary, or directly you may draw the shear force and bending moment diagram. You already studied shear force and bending moment diagram. Okay. So with the help of this you may draw this diagram, shear force and bending moment diagram. Then finally in the question they asked about draw the deflected shape of the beam also. So it is drawn from the bending moment diagram. So from the diagram, so at the support A, so moment will be 80 kilonewton meter. Okay, fixed end moment, hogging moment. Okay, it is a fixed end, it's subject to hogging moment. Okay, 80 kilonewton. After some distance, so point of contact flexure is there. Then at the support B, bending moment will be 0. Then support C, moment will be hogging moment minus 40 kilonewton per meter. So from this, so this portion is like this. Then sagging portion. So this curve is like this. This is point of contact flexure. This is sagging moment. Then this point B point exactly moment 0. Okay. So this point also point of contact flexure. Then BC portion is subjected to hogging moment. So therefore curve, hogging curve. Then CD also hogging moment. Okay, like this. So this is our probable deflected shape. So probable deflected shape is mainly based on the bending moment diagram. Okay, mainly based on bending moment diagram.